Okay, I have one more video as complementary to the previous video in Bayesian rule. This video is about using naive Bayes to classify a continuous dataset problem. In the previous examples, when we were discussing about naive Bayes, in the previous video, we were talking about discrete dataset. This video, we will discuss a bit about how to deal with continuous dataset. What is continuous dataset? I will explain it in the next few slides. So, okay, the tool for naive Bayes problem in a continuous dataset is exactly the same like before. We are using Bayesian rule. Right? So you know about this equation, it's Bayesian rule. The only difference for continuous dataset is as follows. Let's start it by recalling one of the examples that we discussed in the previous video when we were discussing about the Street Fighter game, right? So if you still recall that case, we want to categorize last time, right? We want to classify what is the fourth action. Well, from practical perspective, basically, we want to estimate what will be the fourth action, knowing the first three action, right? That is what we do in a Street Fighter. But from naive Bayes classification point of view, what we are doing, actually, we want to classify the fourth action based on the three known previous input. So it's a classification problem, basically. Okay. Okay, but now we are dealing with continuous dataset. In the Street Fighter problem, we have discrete dataset. I will talk a bit about discrete and continuous in the next slide. But one thing that I want to highlight here, because we are dealing with a continuous dataset, so when we need to calculate the probability, we need to have an assumption. In the first step, we need to have an assumption whether the data is normally distributed, uniformly distributed, distributed in following the Poisson distribution or any other distribution. We need to have an assumption of that. If we have an assumption of normally distributed data, so in order to calculate the probability of each action, we have to rely on the probability density function. Okay. In this example, in the next example that we are going to discuss, let's just concentrate on normally distributed data. So we are going to use this probability density function. Okay. Perhaps the easiest way to give an illustration what I meant by continuous data set for naive Bayes problem is by looking at this example. So here I have 16 samples, 16 training samples, where these 16 training samples are the collection of data of height and weight of 16 different persons with 6 different categories. The categories are a child and an adult. So out of this, if you look at this data set, out of these 16 samples, I have 4 adults and 12 children. Yeah, I have 12 children and 4 adults here. And then I collect the height and weight of all of 16 of them. And then I want to develop a naive Bayes model. In such, based on this height and weight, I want to estimate the classification. I want to classify the person, whether he or she is a child or an adult. But if you look at this, the height and weight contain continuous data, continuous variable. So all of these are continuous, right? Why do I say it continuous? Just let's contrast it with a Street Fighter case. There, I have a class as a category that I want to model, that I want to estimate at the end. And then I have three inputs in our height weight problem that I just mentioned. I have only two inputs, height and weight. But in Street Fighter case, we have three inputs, action 1, action 2, action 3. But if you look at one of the action, let's say action 1, there are only three discrete types of input. I only have three possible inputs in this action 1, either punch, kick, or special. Same thing to action 2 and action 3. I only have three discrete possible inputs, punch, kick, or special. While in our case here, if you look at one input height here, the input might vary infinitely because it's a continuous, it is a continuous variables in the height and in the weight here. So we cannot solve it simply just like what we did in Street Fighter case. But of course, if you have another representation of this data, let's say if I can represent also this data in this way, in this manner, instead of having a continuous variable in the height and weight, I also can represent it as a discrete variable, short, medium, and tall. So for instance, in this height, I have three discrete possible variables, short, medium, and tall. For weight here, I only have two, light and heavy, sorry. So in this case, we have a discrete case. In this way, if you have this kind of problem, you can solve it like how we solve it in a Street Fighter problem. It's very easy. We did it before, right? In a Street Fighter problem. But now we are going to solve it for a case of continuous data set, continuous problem. So the height and the weight here contains continuous variable. And then the category, we only have two categories here, child and adult. And then now the problem of this example is, based on these 16 samples, how do we classify a new individual? So apart from the 16 sample, let's say now I have a new individual where the height is 172 and the weight is 57.5. And then I need to classify whether he or she is an adult or a child based on this 16 samples. So the first thing, then I have to develop a naive Bayes model first based on these 16 samples. And then once the model is developed, we can classify the new individual. Let's try to digest first the data that we have here. So in this case, from these 16 samples, we know that we have two classes that we need to categorize later on for the new individual. The two classes are adult and child. And then I have these 16 training samples containing height data, HI, WI, the weight data. Both of them are continuous. And YI is the target category, which is the class, either child or adult. We have 16 samples, so the I here is from 1 to 16. And then the next simple things that we can calculate is the class probability. We have two types of class, child and adult. We can easily calculate the probability of these two classes. So this is pretty similar to what we did in a Street Fighter case. In the Street Fighter case, we have 12. We have 12 training samples. We have 12 training samples, and then the class that we are going to estimate later on, out of these 12 class samples, we have 1, 2, 3, 4, 5 punch. I put it here, I note it here. I have 1, 2, 3 spatial, and then I have 4 kicks, 1, 2, 3, 4. So the probability of a class punch is 5/12. The probability of class spatial is 3/12. And then the probability of class kick is 4/12, right? So same like that, we do the same thing. Out of these 16 samples, if you look at the category here, the class here, we have 4 adults. So 4 out of 16 is 25%, and we have 12/16, 75% of probability of having a child in our samples. And then the next steps, of course, same like in a case of Street Fighter, we need to calculate the probability of the height of a child, height of adult, weight of child, weight of adult in this case. But probability in here is not as straightforward as how we calculate the probability in the Street Fighter case, because in the Street Fighter case we have discrete variable. But since we have a continuous variable here, we have first to make an assumption how the data is distributed. So let's say again, if we have agreed that we are going to consider this case as a normally distributed data. So if this is normally distributed, then the probability we can represent it in a probability density, right? It's a normal distribution, so you can represent it as a Gaussian probability density function. But if you have normal this probability density function, this function only takes 2 variables, right? When you want to draw the probability density function of normally distributed population, all you need to have is only 2 variables, the mean and the standard deviation, right? So in that case, then, in order to be able to evaluate the probability of all of these inputs, the height of child, height of adults, weight of child, weight of adults, we need first to calculate the mean and the standard deviation of each of them, where x here is the input type. So x here can be height or weight, height of weight. So x is height or weight, where class here is the category, child or adult. So in this case, then we will have mean of height for child, mean of weight for child, mean of height of adult, mean of weight for adult. So we will have 4 mean values and also 4 standard deviation values. These two represent the probability density function of height of child, weight of child, height of adult, and weight of adult. Okay, so we use this. We have to calculate these 8 variables first. So I have already calculated for you. So we need to calculate first the mean of the height of a child. So we have 12 samples here. So I just calculate the mean. I divide it by 12. I sum all of the height, 57.4, 59.57, all the way until 156.69. I sum them all and then I divide it by 12 because I have 12 child samples, right? And then I do it also for the standard deviation. I do it also for the mean and standard deviation of the weight of child, as well as for height of adult and weight of adult. Please take a note here, I only have 4 samples for adult here, so I divide it by 4. So I have these all 8 parameters now. Next, let's take a look on how these data sets, the 16 data sets, are distributed in our population, in our sample here. So here I plot the height of all of these 16 samples, again the weight. But here I indicate with different color, blue for the child and red for adult. If you take a note here, there will be 12 blue dots and there are 4 red dots here. 2 of the dots here are almost coinciding one to another. Okay, now let's take a look on how this data is distributed first. First, let's take a look on how the weight of a child, so the X value of the blue dots, let's take a look on how this weight of child is distributed. So what I'm going to do, I will just project all of the blue dots in one axis, in horizontal axis. Yeah, it's like this. So I just project it here, and then based on my assumption that the data is normally distributed, it should be denser at the mean value there, and then based on the mean value and standard deviation of the height of child that we just calculated in the previous slide, I can sketch the probability density function. So it will be something like this, right? And then I do the same thing for the height of child. So I project it in vertical axis there for the height of the blue dots. And with the same assumption that the data is normally distributed, the probability density function will also be like this. Now, how these two probability density function will look like in three-dimensional form if I combine these two probability density function, and then I will draw it here. It will look something like this, right? So I just combine these two probability density function, and this basically is the contour of the projection of this function to this function. So I just project these two functions to each other, and then we will have this hill, but this is just the contour plot. So this is if you look in three-dimensional view, then this should be a hill where or a mountain where this center of the circle is the peak of the hill, right? So this is how the probability density function of height and weight of the child looks like in contour plot. I will do the same thing for the adult. So I projected the weight of adult, height of adult, and then I combine it, and then I plot the mountain. I plot the hill. Right? So this again, this blue contour basically is the joint probability of the weight of adult and height of adult. Okay, so it looks like that. Now, back to our problem. We have a new individual where the height is 172 and the weight is 57.5, where if I plot it in this 2D plot, it will be somewhere here. The question now, how should we classify this new individual? Is this classified as a child or as an adult? So that is the problem that we have to solve. And then we are going to solve it using naive Bayes approach. If you still remember how naive Bayes solved this problem, basically we just need to calculate the probability of adult given this new individual. We just have to calculate probability of adult given this new individual, and we have to calculate the probability of a child given this new individual, and then we just need to compare these two probabilities. The conclusion will be this new individual will belong to a class where the probability is the highest. So we just have to compare these two probability values. If probability of adult given of this new individual is higher than the probability of a child given of this new individual, then this new individual will be categorized as an adult and otherwise. Okay, so let's try to calculate the probability of adult and probability of child given this new individual. Okay, the approach is still the same. So how to calculate this probability? So like what I just mentioned, you just have to calculate the probability of child given this new individual and probability of adult given of this new individual. Just compare these two, the highest is the winner, and then we can conclude that the new individual belongs of the class where the probability is the highest. How to calculate the probability? We just use this expression based on Bayesian rule. We discussed about this in the previous videos, right? How we came up to this calculation. But the problem now that we have to face, before that, I need to mention, if you look at these two formula, the probability of child given of the new individual and probability of adult given of this new individual, if you compare these two equations share the same denominator. If you look, the denominator are the same, right? So since what we need to classify the new individual is just to compare which one is largest, we don't have to be bothered with the denominator because the denominator is the same, right? So let's just compare the numerator. So which one is largest, then that will be the winner. So that's the first thing that I want to highlight in here. We don't really interested in we are not really interested in the quantitative probability value. We just want to define which one is largest. So let's just calculate the numerator to make our life easier. Okay, so we just calculate this value and this value to come up with a conclusion. The second thing that I want to highlight here, how to find the probability of all of this, the probability of the new individual given it is child and probability of the new individual given of adult, these two variables. How are we going to calculate these two values? Since the data that we have is continuous. If you have continuous data, the probability is represented by this probability density function, right? Let's say if you want to calculate the probability of this variable, let's say, looking at this probability density function, we cannot calculate the probability of this value by itself. Why? Because this probability this tell the density of the probability. If we are dealing with continuous data, the probability that we can calculate is only a probability of the value to appear between two limits. So how to calculate it? You just have to calculate this area. The total area, of course, if you still remember, the total area below this, under this probability density function will be equal to 1 or 100%. And then this green area basically then will tell us the probability of the value between this limit and this limit to appear. So in continuous case, we cannot tell the probability of one single variable to appear, but what we can tell is only the probability of a variable between two limits, two boundaries to appear. That is the case of continuous data sets, right? So that is the difficulty. Then how to calculate the probability? We don't have the probability as per se. What we have is only the probability density. But again, the good thing here, we are not really interested in the quantitative probability. Our interest is only to have a relative value to compare which one will be the largest. So instead of calculating this probability value, the area, we just need to calculate the probability density. We will just compare the probability density, and we are not going to compare the probability. Okay, so once more, we are now, because we are not really interested in the quantitative probability, so we just need to calculate the probability density of the value, let's say Z here, to appear, and we are not going to calculate the real quantitative probability of Z to appear. So we only calculate the probability density here. Okay, so this is the second thing that I need to highlight. We are not going to really calculate the probability of child given the new individual, neither the probability of adult given a new individual, but we are only calculating the relative probability based on the numerator only and based on the probability density. Okay. Okay, now let's start it by calculating the first one, the probability of child given the new individual. Again, as I have already mentioned, I will disregard the denominator here. I will just calculate the numerator. So we are going to calculate this one. The second term here we have already calculated before, right, in the previous few slides, where the probability of a child is 75%, right? We calculated in straightforward way. Now we just have to calculate the probability of the new individual given it is a child. How to calculate that? We use the chain rule. We discussed about chain rule in the previous video. So we just use chain rule. If you need to refresh your memory, you can pause this video and then go back to the previous video and look at the chain rule story there. So, but then basically, how to calculate the probability of new individual given it is child? It's just basically calculating the probability of the height of that individual given it is child multiplied by the probability of the weight of the new individual given it is child. So we are going to calculate that, but remember again, as what I have already highlighted in the previous slide, we are not going to calculate the probability as per se, but we just calculate the probability density here, because again, we don't need the real quantitative probability value. So how to calculate that? We just based on the probability density function, just based on the plot of the normally distributed function, where the probability density function is represented as this formula, right? The one that we discussed in the first few slides, I think. So I can calculate the probability again. Be careful again here. Actually, this this representation that I wrote here is not correct. This is not a probability, right? Again, but this is the probability density. Okay, so well, technically this is not correct because what I calculate here is not the probability, but it's the probability density. But okay, you know what I mean. We are going to just compare qualitatively which one is the highest, so we don't really care with the real probability value. So the probability, but to make it clear, let's call it the probability density here. So the probability density of the height of the new individual given this child, we can calculate it with this function. We have already calculated the mean value. We have already calculated the standard deviation and the mean here. So we can calculate the probability density of the height of this new individual given it is child, then it will be equal to 0.0014 after you calculate it. And then I do the same thing for this probability density, to be precise. It will be equal to 0.0308. Okay, and then there I can calculate the numerator part of this probability value will be equal to this, right? 0.0014 times 0.0308 times the probability of the child, 75%, the one that we calculated before. And then next we have to do it similarly for the probability of adult given the new individual. Same like before, I will just calculate the numerator value where we know the probability of adult is 25%. We calculated before in the previous few slides. And then we need to calculate this part. Using the chain rule, we can calculate it by multiplying the probability density again of the height of a new individual given it is adult times the probability density of the weight of the new individual given it is adult. Okay, so based on the probability density function, I can calculate those two. The result is equal to 0.0236 and 0.0067 respectively. And then from there, I can calculate the numerator of this value. It's equal to 0.0236 times 0.0067 times the 25%, which is the probability of the adult from our training sample. And then the last one, I just need to compare these two. Again, the denominator are exactly the same, so I will just compare the numerator. It is clearly seen here that the second one is larger than the first one, so our conclusion is the second one is the winner. So the final conclusion is the new individual will be classified as an adult.